Well, good morning, everyone. My name is Roger Fritz. I'm going to give this presentation today. Barnaby's Start is going to join us. My partner from England is going to join us a little bit later. He had an issue this week where he overlifted something, and he's got to get back from the chiropractor. He's not doing quite as good as he wanted, so he's going to jump in about the middle, and then he's going to jump in and take over and add some added points. But we'll go ahead and get started. I always like to start the project or these webinars. What I learned from National Grid actually is it's very important to talk about electrical shock hazard. When we're dealing around high power voltages, it's an invisible source. You can't see it until you touch it, and then you're gone. So we always like to bring that up just to reiterate, if you're not really familiar with being around high voltages and things, definitely educate yourself in that area before you start digging into this kind of equipment, because it can be dangerous, but it's also what I found over my career of 40 years in this stuff too. It's actually also kind of an enlightening product. So a little bit of background on myself. My father started in wind charges in 1953, went on to build motor rebuilding companies all over the Midwest of the United States. I'm second generation. That's my fourth generation grandson over there. I'm working in one of my son's 508 UL shops in the Midwest. I've spent almost 40 years in the VFD technologies and electric motors. My father did motor rebuilding up to 5,000 horsepower. My brother runs in those companies in the Midwest. I also want to make sure that you can, join. There's a group called the Nikola Tesla's collaboration group. People from all over the world. There's roughly now about 2,500 people in that. But sharing concepts, ideas to basically continue education that will help people grow and learn further, but also go back to the original principles of how they're originally thought of and designed. And that's what this is this is the access point to that group. I can send or post a link to that later. And I'll post that on the page that was developed for this class. I'll post that on there so you can get access to go into that group. I really feel that he wrote the Bible on alternating currents over the years, and I've actually got a copy of one of his original books from 1908, I believe it is, that he had written, that has a lot of the multiple pieces of technologies about motors and controls. He was a man definitely way before his time. He also created a lot of things that people weren't aware of, that other people took credit for, but I highly believe in his concepts and ideas. I'm going to run a little quick video of his.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the
So what basically came out from that is that he had, taken the generator, which was a alternating current device, put a magnetic rotating field inside of it, and was able to create, sine wave power, alternating current AC. And from that, there's been many things done, to create various types of electric motors, and transformers, and it was an amazing understanding of technology. So what I'm going to focus on today is a lot about VFDs, but I want to start where we started from, which was originally we were taking that sine wave power and bringing it into, basically three phases sine wave power, bringing in L1, L2, and L3 in a magnetic starter through a regular set of contacts here, shown in here. This is an overload, and then went directly to the motor. Advantage of it was basically simple, but disadvantages was the inrush current, that when a motor started across a line like that, because it wasn't creating its counter EMF back to the line, you would get anywhere from 4 to 6 times the running current. So if the motor is rated 100 amps, it would take 400 amps of power to start it, which took a very large generator. Sometimes almost 600 amps to get it just short term to get that thing up and rotating. So then they, started out with, such things as part winding start, where they started half of the winding and then brought the other half of the winding in. That cut it in about half, for power. Then they rotated, and they found out they needed more torque, out of the motors. So they ended up going to Y delta start, which were basically connecting the motor leads, so that the voltage drop across the coils was less. So like a 480 volt motor would put 277 volts across with the way they had connected it, and then shift it afterwards, then back to across the line and give it full 480, and that would give it full torque and power. That was the main focus. So that's what was done, definitely prior to the inverter technology that's been built. Then actually came out from NASA. There was a NOLA device created, which was basically just taking, instead of having the power lines, coming directly in through a starter to the motor, they used SCRs or triacs in here to basically be the power source to the motor. The advantage of that was you were able to ramp the voltage and frequency up. Disadvantage is you weren't able to really change the load on the motor wherever it was. So it was kind of a fixed, again, back to fixed speed, catching up with those, 60 hertz power, or in Europe, 50 hertz power, 380 volt. And so from that, they went to the soft start devices. They were very simple. You basically had and they're still available. There's, you got your 3 legs in, your 3 legs out. Then you just have a simple control circuit here where you can, turn it on or off, or that also gives different stages of acceleration as you want to soft start a motor. And these have become very, very good in the pumping industry, limiting water hammer, controlled start, controlled stop. Also, on the stopping, you're able to regulate that sine wave down. So you're also able to, slow the motor and almost create a braking effect, to get rid of some of that mechanical energy that is, coming through. So this is a diagram of pretty much the standard soft starter, where they normally have a contactor or a disconnect switch, ahead of it, goes directly in. It's got a thermal overload built into it. And then it has these, 3 sets of SCRs that are basically just switching and turning the waveform, again, back to that waveform that's coming off of the generator. They can control and turn when they're turning it on and when they're turning it off. They're a very cost-effective, technology technology today. Everybody, tends to move right away to VFDs, which I think there's a kind of a little bit over push on VFDs. because there's some disadvantages to variable frequency drives that we're going to talk about also a little bit further into the discussion. So then what came forward is the actual variable frequency drive technology, which is basically a bridge diode front end going. They typically have a reactor or a coil, choke coil in here to slow the current down to what it's for. And then they have capacitors to build DC. So that's what originally Edison was talking about is, everything should be DC, DC, DC. But you can't transform DC or control it like you can with, AC power. So then, there's, output transistor blocks, which is really the simplicity of what we're really dealing with. And that goes to the motor. But what we're actually building is we're building DC, and then we're building PWM, pulse width modulation, going out. There are a few other technologies out there, but this is the prevalent one in the industry. So we're taking the sine wave power, going to DC, and then we're building pulse width modulation. And this is all done with firing circuits that are inside the drive control. And then this is an idea of the main transistor. A lot of people don't realize, but there's only about 4 major transistor manufacturers in the world. So a lot of VFDs you're getting are the same as somebody else's on the mainframe components. And where they differ is in the control circuits. So again, the converting to power with a bridge diode, which is basically just it's a one-way conductor. So as this waveform goes positive, it'll only allow the current flow to go this way. It won't go negative. When it's a negative, it won't flow that way. And then when it goes the other way, the negative goes to the positive. So it ends up creating a way to create a ripple DC, and then they have to have the capacitors inside the VFD to smooth out this power, because we want it to be, very smooth before we're starting, to start pulse it through transistors. And the evolution of transistors, I've seen it from when I started back in 40 years ago, doing a lot of work with Toshiba. They were all GTRs, which could only fire, some of them originally were like 6, we were able to fire it 6 times in a waveform. Now they're clear up to as many as 15,000 pulses here, which make a much cleaner current waveform than what was doable before. So that's a DC bus, filtering of the power. And so, a lot of people, have to really understand that we're not dealing with sinusoidal power anymore. We're dealing a lot with this pulse width modulation. The same thing's coming off of, solar, uninterruptible power supplies. And so, from that has created some issues that, should be discussed a little further. So as you can see here, when the power comes in through that diode circuit that we talked about, the outer waveform is the voltage, supplied from our source, the alternating current. This isn't actually showing a drawing or actually a reading of what the input current looks like. So you can see, because these diodes are pulling power at different sequences, we get different ripples in here, and they call that harmonic noise, carrier frequency. I mean, not carrier, harmonic noise. That is in different frequencies than the 60 cycle or the 50 cycle power supply we're providing. So this ends up being, like here, this will be like 120 hertz current. I'm going to go to another picture. I'll go back to those further. I guess I won't. So I'll discuss that a little bit later. But what the issue is that, so this actually creates some ripple, and it also affects the voltage. So that's why they came out with the IEEE 519, harmonic, requirements for applications, because this is a look at a waveform of the input after it's had multiple drive issues, supplied to its circuit, and or all other solid state devices in a plant. And So again, what we're doing is with the transistor output of the drives, we're basically controlling these waveforms. So instead of being a fixed 60 cycle or 50 cycle power, we can regulate this power. As you can see here, we can regulate it to 30 hertz power, 20 hertz power, 10 hertz. We can also go up to 40, 50, 60, all the way through the range. A lot of this is used even for high frequency. If you want to run a motor, instead of running one fixed speed, and you want to run it up to, double its speed, all we have to do is turn it up to 120 hertz. But you have to be aware of all the, mechanical restraints, in your equipment when you do that. This is more of an idea of what the output pulses actually look like. So it's important to understand, that this pulsing, that the motors are actually capable of handling the higher peaking voltages. So some of the earlier installations and motors were like, let's say 1,000 to 1,200 volts peaking. Well, they were seeing maybe 750 volts with a straight sine wave maximum peak. And with some of the PWM that's out there, they were seeing, peaks all the way up to 12, 13, 1400. And what happened, it would do damage to the motor. So what I want to go into is where I started from. I was in some of the first generations variable speed drives that were made by Toshiba back in the early 80s. And I was trained a lot. And their main circuit is identical to the main circuits that are still going on today. They have, the capacitors in here. They did add a soft start capacitor because it was, inrushing too much current. They have the link choke, but the diagram is very similar, to what has been around for, throughout the whole time. And even today, many of the undercomponents inside the drives are very much similar. The only difference that they changed is from the gated transistor, they went into an isolated gate, which basically helped the reliability of the transistor part. So before the microprocessor, we had to do it the old way. It was all, analog potentiometers. So we were actually had to take voltage readings and power readings constantly. And then these are all here, little dial potentiometers that were inside. You had these little screwdriver in there to basically control what this is, the firing processor, to the controller. So it was a control board that is basically just controlling when those pulses are coming out of the transistors provided to the motor. So again, you'll see the main circuit up here is, pretty much identical. And, we had, under voltage, over voltage detection, which was basically just sensing, and we set where those trip points were so it could, signal relays and those things. But everything was done. There just wasn't the digital processor, do all those things. Everything was done with a, regular contact switch, potentiometer out here, our 4 to 20 milliamp signals. But it just wasn't. You had to set your acceleration, deceleration, your upper limit, your lower limit, your high voltage, your lower voltage, your frequency, that you're aspiring to. So all of that you're basically just controlling the regulator board. And this again was the way the pulsing looked at. So you can see the firing on the old GTRs was a lot slower. And you would actually hear the audible noise in the motor. The motor would get a metallic whine to it because you were hearing the frequencies created, by this other type of power supply. Again, the current waveform was pretty sinusoidal. And then, over time, it's grown dramatically. Again, but the same thing is you've got some sort of a disconnect switch. Sometimes they'll put a magnetic contactor for bypass in there to run directly to the motor. They have then the power goes down, it goes 3-phase in, 3-phase, basically out to the motor. And then you got also connections to go out and tell other inverters, what's going on also. And then here's the DC reactor, which is back to the original circuit diagram here, which is here, which is very similar. Some people put what they call line reactors on the output, and I'll tell you why in a little bit. There is basically to calm down this output waveform, and they also put reactors on the front to calm down some of the pulsing that's going in, to keep them into IEEE standards. A couple questions here at this end. Yeah, so one asked if we could get the PDF format later. Yeah, I'll get that to everybody. Let's see. Then, over time, what's evolved is what I see, what scares a lot of people about VFD technology, is these keypads that have, tons of, information on them, details, a lot of information that is very complex when you look at it from that point. But if you go back to the basics, of what you're doing with an electric motor, we're wanting to, slowly bring the frequency and voltage up to the motor. That slowly makes it start. You want to slowly bring it down. And then, came about, where you could get TAC feedback. So in like extrusion applications, you can actually put the TAC feedback into the microprocessor, and it allows it to handle a lot more things. But the thing that I really recommend people to do is, to get familiar with them is don't be afraid of them. They have a ton of information. I mean, some drives have as many as 300-400 parameters that you can play with, inside of them, which is way deeper than what I think is necessary. And I think sometimes they like to make them, complicated, and they can do, all kinds of Modbus and RTU and, connectability, and, everybody's focused on that part. What I really try to focus on is what is the motor seeing, what it's getting, how it's functioning, back to the simplicity, of the applications. Because this tends to, put fear, in people. A lot of people get familiar then with one drive, and they're kind of like, oh, well, I don't know if I could, deal with other ones. A lot of the schools don't really go back to some of the basics. They try to jump in and, talk about the bells and whistles, but, there's just, various, control. I mean, it's got monitor screens, it's got a program key. So as you push the program key, it allows you to go into the various sets of parameters. This is just a shift key that allows you to shift it up and down, just like a typewriter does. It's got a reset button on it, in case, these do have a lot of fault, codes and information written into them to make it a better product. And then these are just, simple up, down arrows. You basically just allows you to scroll through the screen. Local remote, meaning that is it going from the local connections on the board, or is it functioning from the remote connections? And then like the function and data key, this allows you to adjust different things, inside the program button. Then this is just a start, stop, forward start, reverse start and stop. They're just, digital contact inputs that allow that. But those also can be programmed, in and out of the circuit, whether you need them or not. Whether you want, people to be able to access this keypad, you can, take functionality to shut it down. So it's, becomes more of a dummy site, just monitor data only. So you can go up, down the arrow, and you can watch your, your amperage. And this is like, a lot of them have an LCD point, but as you scroll up and down, you're just scrolling, between, this may read the voltage, it may read the amperage, may read the pressure setting on a pressure transducer. It may read the, analog input reading off of a sensor. It can tell you, here also this shows a lot of little indicator button lights, which are pretty simple. All it does is as you move this up and down, this just scrolls through. It's read the amperage, the voltage, percentage, you can actually even read the contact IOs, meaning the inputs, that are going to the board. You can, adjust it from there. The, other, main factors inside of a drive is, cooling, because we are firing the transistors, and there are some losses in those. And so we do create some heat. So one thing I found in, life of a VFD is to make sure that you follow the tolerances of, distance away from another drive, and what the cooling area is of that, of that component, what is recommended to stay, a certain temperature. They don't like a lot of high heat. This is a little bit more about the menu section of it. Again, the simplicity. I like to find almost every drive has what they call a quick start menu. And that is normally set up, if it's a original piece of equipment, it has a set of macros in it that are pretty much just opens up to the parameters that you need to deal with for that given piece of equipment. Because they're used on so many different pieces of equipment, from servos to very simple technology to encoder feedback and reverse direct torque, constant reversing. They've been able to use with this these microprocessors have been able to enhance what it can be done. But that's where it becomes fearful for a lot of people, because they go, oh gosh, but if you look at the quick start sections of the menu, get the voltage hooked up to the unit, understanding how you scroll through the programming and what you're adjusting. So this is like the sections of the display that it again outputs. But I always like to go back to my simplicity part of it, because again, all we're doing is really controlling the frequency. We're controlling the output voltage amount as we're giving it the frequency, which then controls the amperage going out to the motor, which you have to keep into tolerance so you don't create, motor's got a nameplate, got the, recommended current flow to it. At that current flow, it's normally at a certain speed, so it's got enough airflow, across it to keep it cool. It's normally got revolutions per minute, RPM. You got your minimum speed, your kilowatt, which is telling what the output power is. It's got whether you're in running, reverse, forward, local remote operation. So this is an idea of what the, again, to take the fear out of it, you've got this is the small control board that's normally put on most VFDs, and they're like inputs to a PLC, meaning that it can take various items. The C is the common of an output relay, and you got C30, A, B. So ones are normally closed, ones are normally open. You can actually select when the functionality of this set of contacts will operate. Then you've got the Y sections again. These also have a set of contacts on them, and you can control again from when those are functionalities. These are all outputs. You've got your C1, which is your 4 to 20 milliamp input. Again, go back to the normal common of the circuit. You've got here where it's a frequency meter, analog output, current output, and then it's got various extra terminals like on a PLC. So what's all in all of that programming of those drives is how to control what all of these functions work. So they operate it, various ways. Then they have various extra contacts on here. So you can also go and communicate to other PLCs. And that's why this is here. Or you can communicate to other, processors and sequencers. So that's when it comes into whether you've got Modbus, CAN open, all the, most of those are very similar actual, what they call protocols, which are just sequences of telling the communications between, the two processors. And then you've got your various inputs here. So as you give a common signal between common and X1, you can program that to have it be the start function. Or you can go a 3-wire where you have to have a start, and then you have this, going to the stop button, and you can have a 3-wire, start-stop connection. And it's all programming. And so again, go back to the basics and focus on that. So these are some various contact points. This one here is about phase loss. I'll tell you about that's because sometimes you want to use the VFD to take single phase input power and actually run a true 3-phase motor successfully. And so you're able to take the power source here, and instead of using all 3 phases input, you're able to use 2 phases, normally line 1, line 3 only. You don't even hook up this. We can still build DC here. The key factor is that these diodes will be carrying more current. So let's say a motor's 100 amps here on single phase, it's going to draw it through just 2 legs, not all 3 phases. So it's going to be 1.73 times that 100 amps. So it'd be 173 amps going through. So the main focus, you got to have these diodes heavy enough. And so they basically normally time on a single phase application, they'll use a 3-phase drive, but they'll just put 2 phases into it. But it just has to be double the size on the input to handle those currents. But the motor will still function, as is. Plus you get soft starting. So it has eliminated a lot of need for, phase converters that are out there, like the rotary phase, they had like capacitor, where they, gave it a, one shot of a, capacitor out of a different phase angle to get it up and turning. They're still running on single phase, but you had to oversize the motor dramatically. Fairly inefficient when you did it the old way. So this is an advantage if you want to use them, on single phase power. Then this is an idea of what I was talking about of controlling those relay outputs. So you had Y, terminals Y, A, and C, and we can set what the purpose of that is. So you can go into the programming through the keypad, and you can just set, I want Y5 or Y5A, I want that to be when the drive, when it's stopped. It'll give a run signal. It'll just tell that contact. Then you can run an indicator light or that thing. The same way, this is just an extracellular relay outputs that are ABC, and it's just a 3-pole contactor is what it, or contact switch. And so it just allows you, ABC again, but there's 2 sets of contacts on most drives, two relay outputs. They also have various other outputs. They have, transistor outputs, if you want to, run a signal off a transistor, or they have pulse outputs that can track how many, pulses output. I mean, they've elaborated a lot of those things to give it various and multiple types of applications. But I see, 80% of the time, 90% of the time, they're not used. And so the other is you can also set, again, you have to go to find parameter H11. It's the deceleration mode. So, you can set, whether you want it to coast to stop or normal deceleration of, ramping it down. Again, it's all the way back to what I was doing 40 years ago with these various potentiometers, those accelerations, decelerations, upper limits, all that's done. All that's just been done. A lot of this has been, redone, put a microprocessor on the front end side, and then it can, jump through hoops and make the motor run, forward, backwards, exactly to a specific point. But again, my dad always said, use the KISS method. KISS method, keep it simple. Everybody understand what we're doing. It eliminates a lot of problems in the field. We can also control this is a normal big function that's normally needed, is your frequency upper limit and your frequency lower limit. So you can actually set when it turns on, at what level will it immediately go up to a minimum frequency. So if you have a pump and you're not pumping water until 30 hertz, you don't want that to, ever allow the customer or the people to run that too slow, or the pump will go into cavitation. There also are multiple other parameters. If you want to go even deeper, you can set this for multi-stepping. So let's say we want to bring it up to a certain speed where it first starts pumping water, fairly fast. So you have two sets of accelerations. You accelerate it up there, and then you transition it up, and then you bring it on up in speed. And that is really done a lot for water hammer, air hammer, belt squeakage, slippage, all to, basically back to control that torque at the proper time to the proper amounts, so the motors, function efficiently. Again, the simple main component parts, of the drive, I went through those. But then, it's really, a lot of people just need to look at their application and what do they want to control, and then come back and then understand the terminology, in the VFDs to actually, make it a very simple solution. It makes it much easier than, down the road. Otherwise, I see things, way over engineered, it's way over complex. And then, when somebody's trying to troubleshoot something, they can't, easily find the cause of it. And so they're scratching their head and they're doing, replacement of products to determine what the fault was. Well, that's not the easy way to do it. So, and then they have, a lot of fault codes inside the drive. Well, it's good to, read up on that and understand what those fault codes really mean. Under voltage, over voltage. But again, those may be the setting in the drive of what the upper and lower limits are, because these are shipped all around the world and they have multiple parameters adjustable for different countries. So that's all based on what their power source is. So the components may be able to handle 480 volts, but if it went to England, they may only be using it on a 400 volt circuit, 50 hertz. So it'll have a different set of parameters. So it's important to realize that you're, controlling this, but again, keep it simple. So one of the things that happens, which is a phenomena that, people became very aware of, I ran into it when I was doing a bunch of work for Milton Bradley Toys. We installed 70 drives on process injection molding machines to cut power cost. And so we, installed like 70 some drives, and this is before they really even, understood of all the other issues that were going on out there. What happened is that from those various firings here and these extra ripples of frequency power, meaning that the current was firing, you create radio waves and noises from that. It's the same way a radio was built. So what happens is you have your fundamental voltage out here, and then you have what they call third harmonics, which are 3 times 60, or 5 times 60. These showed up. or 7 times 60. And these were the ripple currents that were actually seen also going into the drive with an oscilloscope. And then you had, a true resultant of current. So the current waveform on the input looked very non-sinusoidal. They call it nonlinear power. And from that nonlinear power, create a lot of issues. So that's when they went back and said, okay, well, let me put, in order to adjust some of these, I went and put line reactors on the front. They put fifth harmonic traps, which are basically just a trap that was designed at 120 hertz that would suck off this power and drive it to ground. And so typically on a 6-pulse bridge, like it's done in most VFDs or DC machines, you'll see this harmonic content. But it's different in every circuit, and it's different dependent on your transformers, your wire size coming to where the drive is, everything, because you're creating a harmonic signal on those wires. It even creates, issues about, wire life. And so it's important to be aware of this, because as everybody said, well, add more drives and more drives. And all of a sudden you had weird things happen. So what was happening is we were starting to do that on those molded machines, multiple years ago, before a lot of this fundamentals were figured out. We're actually seeing, low voltage color feeders, that fed the color of the molding product were changing color, because they were, 12 and 24 volt DC circuits that were, ungrounded. These noise levels would, show up in the circuits. And what would happen is it would change the fundamentals. So a lot of electronics have got a lot better, and they've eliminated, some of these things, but there are some weird phenomena you have to be careful. So again, this looks at a spectrum order of, from that firing, what happens. So you can see your third isn't too bad, but that fifth, can be, like 23, 24% of the fundamental current. So if you have 100 amps, you could have also, 25 amps of this current showing up in, in the circuit. And then it attenuates all the way out, clear to, the 49th and 50th harmonic order. And harmonics are no different, So what I found over time is it's very important that we also meter what's going on. And so I've really found, again, something I'll come back to. I found that it's important to, find the proper type of metering. I found that this Fluke equipment is extremely good, and I'll just run a quick video why it is.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using 3-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance in harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative.
So what actually happens is it actually allows you to go in and see that voltage form, that pulse that's going into drives. This can be either from a DC machine or an AC machine. So we can get back to the fundamentals of what is happening, to that original, waveform that Tesla was talking about. That we're basically, getting this off the generator. Well, what are we doing with it, and where are we driving it back to the motor? And motors like this to be calm and peaceful, and that's where the life of the motor is dramatically changed. And so it's important to understand all the pieces. Everybody wants to sell a VFD for everything, and but you got to be careful of the total package, both the torque load all the way through. I want to get to this. My father used to be a chapter president of ISSA. This is a little book I highly recommend you get a hold of. It's out of St. Louis. But this was started in 1944, this group, and it's electrical repair people and motor people that have gotten together and created this massive organization of about 2,500 companies in the United States. Worldwide, it is around maybe 4,000. And they're all motor people that have actually seen the effects of all different kinds of equipment and over years. And what happens too often is we want to design something for cost effectiveness, but we forget to take into effect. So like the fellow at Fluke was talking about, is there's a chart in here that talks about when compared to the nameplate, where are you on balance of those three-phase input powers, and where do you have to derate the motor? So even if you're off 5% in voltage on balance, you're supposed to be derating that motor to 75%. And most applications don't do that. And so I see a lot of motors, they're running in, bad points of their, power input, and causing premature failure. So it's important to do that. It also talks about, all the various functions of what the nominal power is to what the actual nameplate is, and where that falls on the curve, where you should derate things. And again, that booklet is, it also has motor currents, amperages, a very well thought out process. So what's happened from that point is, after we get to the VFD and you create that PWM, it's important to also understand that when you get a distance away from a variable frequency drive, that you also take into consideration what does that output waveform, actually look like, and where are the peaks going to. So there are also a need for a lot of what they call harmonic filters that are, there's various types and brands out there, but what they are is another set of coils, which are inside here, that are inside the circuit. They're going in series with the load, and then they have a group of capacitors in here that are tuned to basically wipe out and clean off these harmonic orders, either on the input or the output. And so the factors that I've also found, in application and design, is that it's very important. This is an idea of looking at those, waveforms before a filter. You can see that current waveform, then you can see the current waveform. After we've, cleaned it up, and all that's happening is that you can see there was 138 amps, 415 volts. So the power load here was quite a bit higher used by the motor than here. When we got it all cleaned up, it was at 443 volts and 128 amps. That's almost a 10 or 15 percent difference in power reduction. Going out to that motor, which all the way goes back to the to the circuit. But one area that I want to talk about is also the which one of the components to use. Do you use a cross-line starter? Do you use a Y delta starter? Do you use a part winding starter? Do you use a soft starter, or do you use a VFD technology? Well, something that's very, very important is understanding that, yes, VFDs will save power because as you slow it down, the horsepower drops by the cube. Also, the GPM goes down. So in a closed loop system that you're on a cooling circuit, it's not as critical as it is on a irrigation system, because in irrigation system, you need to stay at the sweet spot of how much head pressure you're going against, and where is the sweet spot of the actual horsepower produced based on what our actual brake horsepower is. So there's always a sweet spot where the pumps like to operate and run. Well, when you slow this down, the sweet spot moves. And so there is a software tool. This is actually developed by a guy named Rob Wilkie, who's out of Australia, that I met. And he's got it so that you can actually plug the various points in. You can set up those various scenarios so we can find out when we change it to that speed, we go to that GPM, it actually then shows where did that sweet spot go, and do you have the right design prompt for that motor based on what your actual load is, so that we get our optimal best brake horsepower functioning all the time. I've seen differentials in just getting people running to the proper part of the pump to save as much as 30% of the power, and then control it properly from there. And you didn't even need a VFD. Especially in irrigation, you got to be careful because you're looking at total GPM. You want to get a certain amount of acre feet of water to the customer, to the job site. But again, they've kind of got complex, all kinds of output filters and that. So they overcome a lot of that by, I'd say, less effective engineering to the pump curves to the application. They overcome it by tweaking it with a VFD, which works, but you're also maybe still creating losses and not operating at that proper head feet. So I always recommend to really go deeply back to your pump people and find out what you've got for a pump. Definitely get it down to get to the optimal efficiency point of that pump, to always look at that prior to, and then there's also software modeling, which has available out there so that you can look at under different times of day and load. And I can get you an access to this for free if you like. This is produced by one of the drive companies I work with, but it allows you to put in modeling of the pump. Is it throttled? Is the valve throttled? Not yes or no? What is the percentage? And it'll actually do a modeling of energy savings that you're going to get. But the problem that this doesn't take into consideration, it doesn't take into consideration the pump curve. So you need to also look at the effects of the pump curve. And I think ultimately, as time goes on, these two will be, gathered together. Again, then the proper metering tools, your straight voltage measurements, that are out there, portable, easy to use, fairly cost effective. And then you got true RMS metering, which means that you're calculating the true power equivalent from all those various harmonic contents and details, because a lot of the straight meters that are out there with an amp meter or a voltage meter, you don't gain any of this ripple. You don't see it. And so it's important that you do ultimately have the the true RMS metering to determine where your real load factors are. And then these are over time, they call them a hobo meter. You can plug them in, leave it into a device, and it's got current transformers, and you can basically control over time. It's for time calculations of applications, whether you have a lot of transition and load or temperature. Just some easy, friendly tools out there. There's also a manual available from ISSA, which is about motor failure. And again, motors tell the story. So this ends up showing here a failure inside of a motor that was from a quick surge of voltage and power, in one phase. And you can see that the high voltages, between these insulated wires here, ended up being higher than normal. So it shorted, an internal core short. This, you can see, because of the various, again, back to that rotating field that was out there, this had 3 of them because it's 3-phase. So the copper looking color here, this tells me that this motor was connected delta and Y and lost 1 phase. And so all the power was trying to run through just 2 sets of the phases. And so the motor just became overloaded and over time just cooked itself out. Again, some of that's preventable by actually, having that, setting on the thermal overloads correct so that it senses it quick enough that the current jumped, so it didn't actually char those windings, because they're only they were designed for 50 amps. You shouldn't be running 75, 80 amps through them over a period of time. It'll just heat the coil and fry it. It's just a resistor, in essence. This shows a slot failure, and this can happen for various reasons, whether it's being, the motor's been rubbing and actually, cause damage to this, the slot insulation. Again, my dad had me, sticking windings and coils and motors like this, back when I was 10. So I played with them a long time. This up here shows a slot failure where it failed, the voltage, got too high, or contamination got in and deteriorated, that insulation, and, that's here in this slot, it got deteriorated. And so it ended up shorting to ground, and you had a ground fault in the motor. And then this is showing where this blue insulation paper is. That's, again, phase to phase. So you got 1, 2, 3 phases here. And it, and this happened to be a 4-pole machine, you can tell, because there's, 4 here. A 2-pole would only have 2 windings showing, not burnt, and then the other windings would all show burn if that was a 2-pole machine. This would be a 4-pole machine. And that's another thing that can be done that a person should look at is when you're designing the systems is, what motor am I buying? Because you can buy a 1200 RPM motor, 50 horsepower, and it'll have a lot more torque than what a 50 horsepower 18 is. And you can put gearing in, but then the gearing, to gear it back down to 1200 RPM, you have losses in the gearing. So you have there. So the ideal factors of things are actually put a high multi-pole winding. They're bigger, a little bit more costly, but the actual effect of that motor, in longevity can be, a great deal higher than what, it is today. So again, inside this little ISSA book, there's a lot of, little formulas, for fans and blowers, centrifugal applications, flow, amount of pressure, the amount of horsepower, so that you can really, get it back to simple again and figure out, the GPM of pumps, where is the efficiency of that pump, and the higher we keep that efficiency of the pump on the pump curve, the better off we are. So I've been talking for an hour. I could probably talk for 10. I love my industry. I'm grateful for my dad all those years ago, making me my wine motors. I'm now 64, but I do love the industry. I'm very involved in motors and controls. we do and get involved in motors from, 10 horsepower to 10,000 horsepower through various partners I have around the world. And the VFD technologies and the soft starting technologies, are key to me. Also, turbine pump applications. There's a lot of different motors that are available out there so that you can buy and find designs that are the best for the application. BMR has done a wonderful job. This fellow right here, I knew him until passed away about a year ago. His name is Dennis Brimmel. He 50 years ago actually started designing for U.S. electric motors. Then everybody went through, okay, I want to downsize the motor. I want to make it quote more efficient. Well, they forget about that we're actually in an environment that's not, the real world is never balanced. So we don't have balanced voltages and powers and things. So that's where they tend to, not last as long. So this company went back to where they've, put the bigger rotors back in them. They put the ventilated cores inside the motors in the stator and the rotor to make the motors run cooler. They put insulators in here because, again, those frequencies, and then they put also grounding rings on them so that when you get about 100 horsepower and you put a VFD on it, you'll create more static noise and information, and that static then wants to run through the bearings, and you'll have bearing failures over time. So it's just important to know that stuff's out there. That's pretty much the end of my discussion for today. I try to give one of these classes. Please join this group if you'd like. If you need to contact me for any reason, it's just at engineering@AC-DC-HOTLINE.com. It's my 800 number. You can also find me on LinkedIn under just Roger T Fritz. I enjoy my industry. I appreciate your time today. I appreciate everybody showing up.
When you
help you in any way, please ask. I'm gonna, open it up for discussion. Let me see. I got one chat message here. I'd like to know if the recording is available. Yeah, the recording will be available. Send me an email. Sometimes I get a lot of people that are connecting. I've got 30,000 LinkedIn members that are all in the motor industry. So I don't mean to be tardy a little bit about getting back to people, but I get a lot of inquiry and information. So I'd be glad to get it. I appreciate your point there, Chip, of for the informativeness. Like I said, I just try to go back to what my dad said, just keep it simple. He was clear back in the day where he was putting wind chargers up to just DC power to run the battery on the radio. And so, we've obviously evolved, a lot. I did spend almost 25 years in the Boston area, working with some of the major power companies, Eversource and National Grid, specifically for learning applications of VFD technologies and test sites. And I still have a son that's based in Boston. I also have a son based in Omaha, and luckily I have 7 grandchildren. So the world has treated me very nicely. And like I said, if you go back to what do I really need? Do I need just to start and stop the motor? Do I need to put just a soft starter in to eliminate that, inrush and control, water hammer or slow stopping it? I think those are the simple and reliable pieces that are in the marketplace, because you don't have much going on to break, and nowadays these SCRs all get shunted out after they're up and running. So they're basically just a standard starter at the end. They're back, just running across the line. The motor's happy, getting good, clean power. But you do have to look, as you are around various industries and application. And, I have a lot of friends of mine in the motor industry that are telling me, today with a lot of the solar and things are going on, the input power that we're getting from the power sources is not clean. So it's good to get that evaluated, and check that. That way we end up, not having, failures, because that's the worst part is you're trying to run a plant, try to keep it running. Seemed like the old plants just ran and ran and ran. Well, they ran and ran and ran because they were simple, but also they were doing things the simpler way. It tends to be today, I think we get oversold, and I don't think a lot of people that are selling certain products are educated back to what it originally was. They want to sell the newest, greatest, certain, protocol to connect to this, and everything's gonna be fine. Or they want to buy these fancy instruments that are going to record and document why the failure happened. Well, if you go back and you test it first on your plant, find out what's going on, then you get your information, move forward. It's just really important. Person say, thanks a lot for, practical points. I'm a practical guy. I grew up in Nebraska. Now I live in California. But, the town I grew up in had like 300 people in. But, this career has taken me around the world. I've been from, China to all over Europe. Haven't been to South America or South Africa yet. Been a little bit to South America, all over the United States, Canada. And what I do find is, no matter what around the world, there's a lot of great people out there. And didn't look like Barnaby got back. We'll definitely get him brought in next time, as we bring on another detailed set of technologies. Again, I try to have a webinar once a month. And if anybody would like to, ask a question, please do. Just open up your mic and, fire away. So.
Hey, Roger. Rod Waller with Hunter Industries.
Hey, Rod.
Hey, very good. This was excellent. Thank you. Hello to all the other guys here.
Where are you from, Rod? You're from Hunter?
I'm from San Diego.
Oh, okay.
Yep.
A few hours
by way of Tucson and Florida and back. Anyway, what we see, yeah. What we see occasionally, on commercial jobs with VFDs is, just a lot of noise. And about all we can do is, put a capacitor across the primary power or something. Often that calms it down, but the finger really points at us at times that, it's our equipment, and, it could be, but oftentimes when we get things separated out and get the VFD tuned, then that all settles down. What do you say? What's our best step moving forward?
I think the best step would be whenever it comes up, is tell them to do. There's different ones out here besides the Fluke, but just get a view of what that voltage from that noise is. Let's see if I can find the slide here. The noise from the VFD is this PWM radio noise that is created. And so that's what we found way back, 25 years ago when we were dealing with Milton Bradley toys. We put all these on, 75 injection molding machines, and all of a sudden the colors of the products were turning different colors.
Right.
They're going, what the hell's going on? And we're kind of scratching our head because the drive manufacturer didn't really explain all that to us. And so we ended up going in, and we had to put some meters on, and then we worked with the power company. But we had to go in and then put line reactors on the front to basically and what I always do is get them to understand this point here. So this is what you're seeing, is you're seeing all these various harmonic fundamentals, and the less amount of VFDs that you have, the less all this happens on your main power circuit. So it kind of becomes not really that important. But the more and more drives you get in, the more and more it becomes prevalent, and the more we get solar, out there on the power sources, because if you look a lot of the ranches and stuff that I'm dealing with around California, they're putting solar up everywhere, and they're giving this output PWM power back to the power company and expecting the power company to filter it all and, to try to get it back. So I've seen also voltage changes from when the solar is on or when it's off. A guy up in Chico that I know that runs a motor company that I trained him in motors years ago. He runs the old company that I had, and he's seen where, on a couple of phases, because they're putting single phase power back on the solar only to 2 phases because it's cheaper than doing all 3 phases. They're putting it back to the grid, and it's changing the voltage on 2 legs up to 600 volts, and it's 480 on the other 2 legs, 3 legs. And that's just absolute no-nos, but they kind of get it by. So I guess back to your question is, have them get a quick meter and show them where these are. You can buy some fairly inexpensive harmonic meters and stick it out there. It's for their best interest too to get that cleaned up, because if you don't, the power losses, if you don't get that cleaned up, even on the output to the motor and the input, as well as possible, you're giving up efficiency, because this motor was pulling the same, but all you got to do is do the math. 415 volts times 138 amps. Do it in my head, but I'll do it on a calculator. 451 times 138. So that's 62 kilowatts. Where if you go 443 times 128, that's 56 kilowatts. Well, if that's roughly 10 kilowatts of power you're wasting. 10 kW times, 6,000 hours equals 60,000 kilowatt hours times, power here in California is
whatever the cost. Yeah.
That's $9,000 difference in it if you're running it 24 hours a day, or 6,000 hours.
That's amazing.
And people aren't even aware of it. They're going, oh yeah, well, I put the VFD on and I'm saving power, but they forgot to calculate the other factor is back to where is that pump curve? Because what Rob showed me out of Australia blew my mind when he showed me that the where these curves go, and the pump guys tend to give you one set of curves. I mean, that's where they're designing it for an 1800 RPM machine or 1550 or whatever, and they're giving them a curve. This is the best horsepower point, and this is the optimal point. So you should run in this tolerance range. But they could do a different bowl stack and maybe have instead of 3 sets of bowls, maybe they go to 4 or 5. When you put the VFD, that maybe they should run together. So I know over time this is becoming more and more informative and helpful, because the power companies had gotten burned a little bit about the energy savings of drive controls on irrigation, because they found out, well, gosh, we put this on, but they forgot to take into consideration the amount of acre feet. So yeah, well, it was pumping 1,000 gallons a minute before at full speed, and then we backed it down to 600 gallons. Well, they still need to get that 1,000 gallons to those crops over a certain period of time. So it wasn't true savings. Plus you had losses in the VFDs and things. So I just want to, people that I want to work with, I want to make them aware of what we're doing, because, the original power that we had, was so much cleaner and better. And the more and more, whether it be coming from wind or solar or wherever, the more and more we become with a, less stable grid and less stable power, the more and more it's affecting motor issues and motor repair. I've got another fellow does that answer your question, Rod, a little bit?
Yes, thank you.
You're welcome. So the guy here said, sorry, Roger, his mic wasn't working. I'm still a novice of VFD, but we are selling in our market in North Carolina. I have been small pressure tanks and bladders with soft starts, potential replacement of the pressure tank. It gets a little tight in some of these enclosures. Yeah. Well, and answer to your question there, Chip, that you asked there. Sorry, your mic isn't working, but the soft start, what you're doing there is, again, that's the simplest mechanism. Because what you're wanting to do is, what he's talking about is a pressure tank, is that the bladder inside the tank before was, helping create, eliminate that water hammer. So this is the best advice. The nice thing about a soft start is you can totally enclose this thing, and it doesn't matter. You don't create heat because you create some only when it's starting, but it's not enough. They're designed properly. And this actually is the best. You want to get the ones that can both control the multi-stage accelerations, in that application, because you want to bring it up. And that's why they have to have more digital inputs, what this is. So you bring it in, once here, and then when it's to a certain amount of time, it shifts to another one, and you have to time that with the pump. It doesn't really get a feedback. You can watch current, and you can automatically, but they've gotten their processors much better. But this does, help as far as soft starting, and eliminates his issue about, as much, required of a bladder, of the old pressure tanks that basically just, absorb that surge of water, and you're mechanically getting rid of it. So I hope you answered your question there, but, and it does eliminate the pressure tank. A lot of it is done now with VFDs and those smaller ones, because the VFDs are a little bit, well, they have a better processor on the front. They're more controllable, but a lot of it is that it self-calculates things, where you can actually get it done on a soft starter. You just have to be a little bit more patient with it, and really take your time, getting used to what the functionality of this is. But I think the answer to irrigation is soft starters, because some of the